In this video tutorial, we're going to review the WEB.BM reporting tools located here on the main drop-down menu, and their purpose is to help us analyze the model output. We are going to be analyzing the Narmada River Basin model output, and its project is defined with a custom time step. This system uses 10 daily time step starting on the 1st of July 1972 and lasting until the 1st of July 2017. So it's a total of 46 years. The 1st of July is the start of the hydrologic year in this basin. If you look at the scenario, you will see the description of the scenario. It's called the base case with 14 reservoirs. We are conducting steady state calculations, obviously, since we're using 10 daily time steps. We will be using multiple time step optimization year by year. To run the model, you click on the solver, select the project and scenario, click on the calculate button, and we will be getting these messages every 1.5 to 2 seconds on the status of how many years have been executed. Now that we have the model output, it helps to review the reporting tools. First, you will see that we have three options here. We have the chart option, which is easier to access from the Google Maps. We have the node deficit tables and channel deficit tables. Let's examine the node deficit tables first. In this option, we start by selecting the project and the scenario. And now we have three options here. If we are dealing with a particular consumptive use node, and this option is only used for consumptive use nodes. These are water users. We are basically evaluating the deficits with respect to either each individual user, and we can select a user from the drop-down list. These are all water users in the system. Or if we want to evaluate them all at once, we can click on this annual deficit for all consumptive use components option. If we select this option, we are not going to be selecting anything in the last drop-down box. When you click on the refresh button, the model will scan the database for a solution for all components, for all some consumptive use components, and it will tell us what annual deficits the model produced for each irrigation block. So here are the names of the blocks: Bargy left, Bargy right. These are blocks that are supplied by the Bargy reservoir. You can see that we have 0 deficits for those two blocks for all 46 simulated years. So our average is at the bottom, it's shown as 0. There are some deficits for some smaller reservoirs, but by and large, all larger reservoirs like irrigation from ISP, OSP, and SSP, their deficits are all 0. Barna irrigation, for example, has some years with deficits. And at the end of the table, you will see the statistics for all years that the average is 4.53%. These deficits are in percentage points, the percentage being the percentage of the annual demand. If you want to save this table, you can export it, or you can copy and paste in Excel. If you export it, you will get this table as a CSV file in Excel, and these will be the same values, which you can now print in your report or use for further analysis. The other option, for example, relative deficits or absolute deficits, which are in the units of flow or in millimeters if millimeters were used, relates to a selected component. So let's select, for example, Barna irrigation because it has some deficits here, and decide to look at relative deficits just for Barna irrigation. The table is now going to have a slightly different format. When you click on the refresh, you will see the 36 columns in the table. And the rows in the table are going to be the simulated years. So now we're going to see the deficits that we encountered in each simulated time step in each year. So for example, in 1975, we had some deficits starting from the third 10 daily period in July, and they were lasting throughout the irrigation season. Similarly, we have much higher deficits in 1976, so 40.53%. You notice that these deficits are evenly spread in all time steps because this is a constraint we set up when we were setting up the model run. In other words, if we have to have deficits, we want them evenly spread out. Again, this is not easy to see all at once because we have a lot of years, simulated years, and a lot of time intervals, but it's easier to download it again and look at it in spreadsheet format. We have one more selection here which is very similar to this, and that is going to be the channel deficit table, which is pretty much the same as this option. Here we only have an option to select a single component. We don't do this analysis for all components at once, and it's going to be either absolute deficits or relative deficits with respect to the selected component. The selected components now only includes channels, so this is a list of channels in the system. And it makes sense to do this analysis only for the channels which had some environmental flow targets. The deficits here will be defined in terms of the deficits of not meeting the environmental flow target. We can now move to the plotting tools, which are a powerful feature. We can, for example, decide to plot some of the channels. Let's say we'll select the channel here. And this channel has an ideal demand of 0. In other words, it doesn't have environmental targets, so we can remove this ideal target of 0. Instead, we can decide to add additional channel to it. So we picked a channel which is downstream of the Bargy reservoir. Let's pick a channel which, for example, is located further downstream, so we can compare what happened to the flows between, say, Bargy and ISP. So here is Narmada above ISP. We're going to select this and add this as a second plot. So now when we click on the refresh chart, we're going to see both plots together. We can use the zoom in feature to zoom in time, and this allows us to move back and forth and see the hydrographs downstream of Bargy and then immediately upstream of ISP. So we can see the difference in flows between the two locations. Now, because these are average 10 daily flows, we can certainly change the setup and look at those as a stepped function. This will get the flow back to the original with all years, but you can again look at individual years by just sliding the ruler left and right. This is a time series plot we are looking at right now, but there is another type of plot that we can generate here, and that is called the exceedance plot. If we click on the exceedance plot, we are going to be asked to set up the starting and the ending time step that we want to look at. The default, of course, is all time steps that were included in the simulation, as you see here. But exceedance curves or flow duration curves are usually interesting to look at for individual months or for a wet season as opposed to dry season. So we can select, for example, here that we don't want to go all the way to the end of the simulated period, but let's just go to, say, the 1st of September. This would cover all of July and all of August. So we were looking at the highest flow months, highest flow 10 daily periods, the 2 months of the high flow season or the monsoon season. If we click on this option and click on the refresh chart, we are going to get a familiar flow duration curve. So 50% of the time, the flows are going to be either at this level or higher. And it's interesting to see that the flows below Bargy are very close here to the maximum capacity of the Bargy hydropower plant, which is 218 cubic meters per second. This is slightly higher because we have additional return flows from irrigation coming downstream of the hydropower plant. This could have been done the same way for a low flow season. And finally, you can have up to 4 channels plotted. You can also plot the same probability curves for reservoir levels. The last feature that is interesting here would be this show flow feature, which allows us to specify any time step or any length or period within a simulated year. It could be several sequential time steps at once. Again, it could be the whole year or just a particular season or even an individual time step. So these are the simulated years. We can select, for example, year 2005 and start from maybe let's pick a dry month, May, and we can again pick 2005 May, but this time we're going to pick the 11th. So we're looking at a 10 daily period between the 1st and the 10th of May. The beginning of the 1st of May until the beginning of the 11th of May is the 10-day period. You click on the apply button. The model will display the flows. In the newer version, this is going to be clearer. Instead of average flow, there's going to be just Q equals. But you can basically check the reservoir balance, and it's even more interesting if you're checking the reservoir balance for output that was printed in the units of volume. In that case, even the reservoirs that are showing its starting volume and ending volume for a time step and net evaporation, they can be checked for water balance for every single individual time step. All inflows and all outflows on the reservoirs are shown, as so is the reservoir storage change. So basically we have information to check balance for every node this way. This can be done again on a seasonal basis. It can be done for individual time steps, or it can be done for entire year or many years at once, in which case we will be getting the average flow over the entire period that we are covering in our selection here. These are the currently existing tools that help with output analysis, and we hope you like this presentation. This ends the current video. Thank you for your attention.